So we've seen that optimization results in Hilbert spaces, such as the Lax-Milgram theorem, or more generally the Stamp-Pacquiao theorem, allow us to solve some infinite-dimensional linear algebraic problems and consequently get solution to partial differential equations in certain Hilbert spaces, such as the Sobolev spaces. Now, in particular, you can prove that if you have any function f in L2 of 0, 1, you can find a unique u in the Sobolev space H1 over the interval 0, 1 that would satisfy the ordinary differential equation second derivative of u plus u of x equal f of x, but not for all x in 0, 1, but in a weak sense. All right, so in the integrated sense that we've discussed before, that is to say that the integral of u of y phi second of y dy plus the integral of u of y phi of y dy is equal to the integral of f of y dy of 0, 1. All right, so in that sense, and that is true, f of y phi of y dy, and that is true for every phi that will be C infinity and compactly supported within 0, 1. So we have this weak solution, but the question is that really a genuine solution? Does the solution we're getting here belong to the space of twice differentiable function? And does this equation hold not just in that weak sense that I've recalled here, but in a classical pointwise sense? And the answer to that question is yes, and that's what we're going to discuss in this little interlude to wrap up what we've seen in the first 2 chapters of the course. And that's, in a functional analysis term, an embedding result. It's a result that tells us that a certain space, namely the space H1 of 0, 1, is included, continuously included as Banach spaces into the space of continuous functions on 0, 1. And that's called the Sobolev embedding theorem in one dimension. That is to say that for every u in H1 of 0, 1, got to remember that H1 of 0, 1 is a space of not functions but equivalent classes of function. There exists a unique u that is continuous on 0, 1. Let's call that u bar. That is such that u is equal to u bar almost everywhere. Right, so there's a representative of that equivalent class of functions u in H1 of 0, 1 that happens to be continuous. Well, it's a representative of that class, so it's equal to u almost everywhere. Right. Now, once we've proven that result, that every function in L2 that has a derivative in L2 has a continuous representative, that's another way of formulating this theorem, we are going to prove a corollary that says that for any f continuous on 0, 1, there exists a solution which happens to be in C2, so twice classically differentiable, and solves the equation not just weakly, but in a classical sense, that is to say for every x in the open interval 0, 1. Now, this is part really of the 20th or 21st century approach to PDE, which separates PDE problem into 3 parts. The first part is existence, the second part is uniqueness, and then the third part is regularity. So what are we trying to do here? Well, first we prove existence by constructing a large enough space of solution for which proving existence is not too hard. We've done that using the Sobolev space H1. Then you might want to make that space small enough such that solutions are unique in that space. And indeed, we've proved uniqueness in H1. And then you might ask the question of regularity. That is to say, is that H1 solution actually better than just being an H1 solution? And here we prove that it is a C2 solution. So we go through these 3 questions, then you can tie them up together even further, because once you have regularity, you can say, maybe I don't just have a solution of the equation in a weak sense, I have the solution of the equation in this everywhere sense. And then once you have that, you can ask questions such as, do I really have uniqueness within that space, which is a much smaller space? But we won't discuss this type of question of uniqueness. This would also require a discussion of boundary values, which we won't do here. So what we want to do just is to use
the Sobolev embedding to go to that third part of the reasoning, the regularity part, and prove that our H1 solution actually is a C2 solution and that it improves the notion of equality to a classical notion of equality.
So to prove this, we start from the weak solution of the problem. So we give ourselves a f that is continuous on 0, 1. And if it's continuous on 0, 1, well, its square is going to be continuous and therefore Riemann integrable. And so f is going to be in L2 of 0, 1. So the Lax-Milgram theorem is going to give us a weak solution. That is to say, a unique u in H1 of 0, 1, such that for every phi C infinity compactly supported on 0, 1, the integral from 0 to 1 of u of x phi second u of y, maybe to be consistent, phi second of y plus integral from 0 to 1 of u of y phi of y dy is equal to the integral from 0 to 1 of f of y phi of y dy. Now, the Sobolev embedding theorem that we are about to prove, and we will get this corollary we're looking at as a corollary of the embedding, tells me that this u, which is an equivalence class up to almost everywhere equality of functions, as a continuous representative, such that u is u bar almost everywhere. Now, if the two functions are equal almost everywhere, then this family of equality star is going to hold for u bar. So we're going to have that for every phi compactly supported C infinity in 0, 1, the integral from 0 to 1 of u bar of y phi second of y dy plus the integral from 0 to 1 of u of y minus f of y, so u bar of y minus f of y times phi of y and dy is going to have to be 0. And now let me remind you what the definition of the weak derivative is. I can also rewrite this as the integral from 0 to 1 of u bar prime prime of y. This is not quite an integration by part because I don't know yet that u bar is in C2. So this has to be interpreted as the weak derivative, the second weak derivative of u bar. But what I have now is that u bar minus u bar second minus u bar, plus u bar minus f is 0 weakly. And it's 0 when integrated against any C infinity compactly supported function. But the only way that you're 0, the only way you have integral of f times g is equal to 0 for all g C infinity compactly supported is if f is 0 almost everywhere. So what we have now is that u second bar, which is a priori just an element of L2, has to be equal to f minus u bar almost everywhere. But f minus u bar is a continuous function. Right. So if you're almost everywhere equal to a continuous function, then you must have a representative which is itself continuous. So there exists a unique v continuous on 0, 1 such that the second derivative of u is v. So that's basically telling me that u has two derivatives that are continuous, so u bar, so that u bar is in C2 of AB. And let me leave that to you as an exercise. This implies that u is C2. And how do you see that? Well, here's the hint, right? You just rewrite, u bar. You just rewrite u bar of x as the integral from 0 to x of u bar prime t dt. And then even if your u bar is only an element of L2, you're going to be able to compute the derivatives of u bar in that way. This limit will exist because it's the limit of 1 upon delta integral from x to x plus delta of something integrable, namely u bar prime t dt, understood in the weak sense. And you're going to show that this tends, sorry, I messed up a minus sign, that this tends to minus the actual derivative of u. Well, that this limit exists, and therefore that u bar is classically differentiable. Then you do that for u bar, and you do that for u bar prime, and you will show that u bar itself has to be C2 because its weak second derivative is equal to a continuous function. All right, so my u has to be C2 because it satisfies the equation, and therefore we have this weak second derivative equal to a continuous function. So the weak second derivative is continuous, and if the weak second derivative is continuous, then the function itself is C2. Right, and now what have we got then? We have that this equality now holds almost everywhere. So let's write it like this: minus this plus that equal to 0. And this function u second minus f plus u is continuous. Now when you have a continuous function which is almost everywhere 0, it has to be 0 everywhere, because the only set that is open and as measure 0 is the empty set. Therefore u is equal to f of x plus u, minus u bar x. I keep moving that from side to side, for every x in 0, 1. And that is to say the equation holds pointwise as opposed to just weakly. Right, so this is the corollary, and you could see how we're using the equation. The embedding of spaces is just going to tell us that our solution is continuous, but our solution being continuous forces its weak second derivative to also be continuous, and therefore the solution itself has to be C2. Now all we have to do is prove the Sobolev embedding to conclude that all weak solutions to such an ODE are actually classical solutions. So how do we prove this embedding of the Hilbert space H1 into the space of continuous function? So let's prove the theorem. We start with an element of H1, and we're going to show that there's a representative of that equivalence class that is an element of the continuous functions on 0, 1. So here is what it's going to be. I'm going to define u bar of x equal the integral from 0 to x of u prime of t dt for all x in 0, 1. And by u prime of t, I mean the element of L2 that exists because of the definition of H1. And this is well defined because I'm on a finite interval, so being in L2 is more demanding than being in L1. So u prime is in L1, L2 is included in L1 of 0, 1. So this integral makes sense, and it makes sense. But I want to show that two things. I want to show that it defines a continuous function to start with, and then I want to show that this function is equal almost everywhere to u.
At least if I add a constant, which is certainly a continuous function itself.
So let's write that up. We need to show two things. One, that u bar is a continuous function, and two, that u bar is u almost everywhere.
Adding a constant if needs be.
So let's start with 1. So let's take 2 points in 0, 1 with x greater or equal to y. Let's look at u bar x minus u bar y. that is the integral in the Lebesgue sense from x is greater than y. So from y to x of u prime of t dt. And what can I say about that? Well, I could use Cauchy-Schwarz inequality and say that this is smaller than the L2 norm of u prime, which is an element of L2 because u is in H1, times the L2 norm of 1 integrated between y and x, which is y minus x to the power 1/2. So this means that u is indeed in the space of continuous function. It's actually better than that, right? Because u bar x minus u bar y is controlled by a constant times y minus x to the 1/2. That's what we call being Euler continuous of order 1/2. So it's uniformly continuous in a very nice quantified way. Okay, now let's prove the equality almost everywhere. In order to do that, I'm gonna get myself a C infinity compactly supported function, phi, and I'm going to look at what I can say about the integral of u bar phi, right? And what I want to show, so what I need to show is that this is equal to the integral of u phi. If this is true for every phi in C infinity compactly supported, because this set is dense in L2 of 0, 1, this would imply that the integral of u bar minus u times g is 0 for all g in L2, which would imply that u bar minus u is 0 in L2, which is the same as saying that u bar is u almost everywhere. It's an argument we've used implicitly a bit before. That's important here. So I just need to test against this test function in compactly supported C infinity function. And if I get the equality for every test function, then u bar would have to be equal to u as an element of L2. So, all right, so let's try to prove that. So what? So we have u bar phi prime of x. So I'm going to start by trying to show this inequality, but not with phi prime. And we'll see that it's a little simpler, and then we'll try to move from the fact that it's true for every phi prime to the fact that it's true for every phi. So how does that work? Now this is equal by definition to the integral from 0 to 1 of the integral from 0 to x of u prime t dt times phi prime of x dx. Now I can use Fibini Theorem. All of these things are in L1, and I get the integral from 0 to 1 of the integral. Okay, t is smaller than x, so I'm gonna go from when I integrate phi prime of x, I'm gonna go from t to 1 times u prime of t dt. Now phi prime is a classical derivative of phi, which is C infinity, so you can apply the fundamental theorem of calculus to that, and what you would get is phi of 1 minus phi of t. But remember that phi is compactly supported, so phi of 1 has to be 0. Okay, now that gives me that this whole thing is minus the integral from 0 to 1 of phi of t u prime of t dt, and by definition of what a weak derivative is, this is equal to the integral from 0 to 1 of u of t times phi prime of t dt. So we've shown that u bar matches u when tested against every possible derivative of a test function. And now we need to go from that to the more general fact that the equality holds when you test against any test function, not just any derivative of a test function. So let's give ourselves a generic element in CC infinity. And we're going to try to express that in terms of a derivative of another generic element. And the way we do it is the following. We're going to introduce a function h as v minus the integral of v, right, times some psi. So I'm going to make things to have integral 0, where psi is going to be a C infinity compactly supported function that has integral 1. Right, so we have in this way that h is C infinity compactly supported and the integral of h is 0 because, well, I've made sure it is, right? I've subtracted the integral of v from v and multiplied by something that has integral 1. Right, so now this h I'm going to write as a phi prime. So I'm going to define phi prime, I'm going to define phi of x to be the integral from 0 to x of h of t dt. All of these things are classically differentiable. And so I have that phi prime of x is equal to h of x for all x. Now what I want to do next is show that phi is compactly supported, because if phi is compactly supported, I can apply the fact that u bar times phi prime, the integral of that is equal to the integral of u times phi prime. My phi prime is h, and my h is almost v, and except for this sort of constant, almost constant term that has been subtracted from it. So I want to show that integral of u bar v is integral of u v, and I'm going to do that by first showing that integral of u bar h is integral of u h, and I'm going to do that because h is a phi prime. Now I know that my phi prime is in C infinity. That's obvious because it's the derivative of, because it's equal to h, and h is in C infinity, so phi is in C infinity. It's not immediately obvious that because h is compactly supported, so is phi, but it is correct. So here's why that is. If you denote the support of h, or you say the support of h is included in some interval alpha beta, and then you look at phi of x for an x smaller than alpha or for an x greater than beta, then what happens? So let's say for x greater than beta. For x greater than beta, phi of x by definition is the integral from 0 to x. Let's say, just keep the definition of h of t, which is equal to the integral from 0 to beta of h of t dt plus the integral from beta to x of h of t dt. But above beta, h is 0, so this is just the integral from 0 to beta of h of t dt, which is also the full integral from 0 to 1, because between beta and 1, h is 0. But h as mean 0, that's a very important condition that we've imposed. That's why we've subtracted something from our generic v. So phi of x is 0 above beta. And if x was to be below alpha, well, then the same is true, because you will get that phi of x is the integral from 0 to x of h of t, but because x is is below alpha and the support of h is above alpha, then I'm integrating 0. So we have that the support of phi is actually included in the support of h, and thus phi is indeed C infinity and compactly supported. Now, by the first step, we have that the integral of u bar against such a phi prime is equal to the integral of u against such a phi prime, and we've just seen that and phi prime is h. That's the way we've defined phi. So we have that times h equal this. Okay, so let's remember what h was. So we have the integral from 0 to 1 of u bar x minus u of x times v of x dx has to be equal to the integral from 0 to 1 of u bar x minus u of x times psi of x times the integral from 0 to 1 of v of y dy, and that's dx. And this right hand side I can rewrite, I'll just change the name of the variables. I can rewrite it as the integral from 0 to 1 of v of x dx times this constant, the integral from 0 to 1 of u bar z minus u of z times psi of z dz. So what is that telling me? This is true for every v c infinity compactly supported. So this is true for every L2 function. So this here has to be equal to that constant almost everywhere. So what we have is that u bar x minus u of x is equal to this constant for almost every x in 0, 1. Now we're basically done here because we've proven that u of x as a representative, which is, so u as an equivalence class as a representative which is a continuous function plus a constant. And of course a constant is itself a continuous function on 0, 1. So that is to say that u as a continuous representative.
And this concludes the proof.